For a long time, antimatter research had a simple but frustrating limitation. Scientists could create antimatter, but they could only study it in the same environment where it was produced. That matters more than it sounds. At facilities like CERN, antimatter is made inside extremely active experimental areas filled with magnetic fields, vibration, and electromagnetic noise. Even tiny disturbances can affect how precisely measurements can be made. And precision is the entire point of this field.
So this here is a non-destructive detection signal. What you see here is in principle a superconducting resonator, which would look like this. But the fact that we are putting the antiprotons to the center of this resonator, the antiprotons short the thermal noise of the detector. So the indication that we have antiprotons in this trap comes from this dip here. And the width of this dip, by understanding the width of this dip extremely well, we can kind of count the particles. And right now we know that we have 92 particles inside the trap.
Because physicists are trying to answer a very deep question. If the Big Bang created matter and antimatter in equal amounts, why does the universe today contain almost only matter? To move forward, researchers needed a cleaner environment to study antimatter, quieter, more stable, and physically separated from where it was produced. The problem was simple. Antimatter is extremely difficult to transport. It cannot touch normal matter. It cannot be placed in a normal container. Even the air around it is enough to destroy it instantly. So it must be held using magnetic and electric fields inside a vacuum, essentially suspended in place without touching anything at all. That's called a trapping system, and it keeps antimatter stable long enough to study it. The breakthrough this week was not the discovery of antimatter, and not even its production, but something much more practical. Researchers successfully moved a trapped batch of antiprotons out of their production area and transported it across CERN campus while keeping it fully contained. The transport lasted roughly half an hour over a short distance, but the scientific difficulty was not the distance, it was maintaining perfect stability the entire time. Even small changes in temperature, vibration, or magnetic alignment could have disrupted the trap. The system used a portable version of a magnetic confinement device, cooled to extremely low temperatures to keep conditions stable. What makes this important is not the scale of the experiment, but what it enables. Until now, antimatter had to be studied where it was created. Now it can be moved to specialized laboratories designed for higher precision measurements. And that matters because even the smallest difference between matter and antimatter could help explain why the early universe didn't cancel itself out completely. This experiment does not answer that question, but it removes one of the practical barriers that has limited how carefully we can investigate it. And in physics, progress often begins like this, not with a dramatic discovery, but with the ability to measure something more precisely than before. For more than 50 years, no human mission has traveled beyond low Earth orbit and gone all the way to the moon. The Artemis II mission is designed to change that, but its purpose is often misunderstood. This is not a moon landing mission, and it is not simply a symbolic return. Artemis II is a full systems test of how a modern crewed spacecraft actually travels to lunar distance, operates in deep space, and returns safely to Earth. The mission begins with launch aboard NASA's Space Launch System, the most powerful rocket the agency has built since the Saturn V. In the first phase, the rocket places the Orion spacecraft into a temporary low Earth orbit. This is essentially a short parking orbit that gives mission controllers time to confirm that Orion's critical systems are working properly before the crew commits to leaving Earth. Once those checks are complete, Orion performs one of the most important maneuvers of the mission, translunar injection. This is the engine burn that pushes the spacecraft out of Earth orbit and onto a path toward the moon. The easiest way to think about it is that Orion is not flying straight at the moon like an airplane heading to a destination. Instead, it is being placed onto a carefully calculated curved path through the Earth-Moon gravitational system. That path is called a free return trajectory, and it is one of the smartest safety features built into the mission. A free return path uses the gravity of both Earth and the moon to create a natural loop. As Orion travels away from Earth, our planet's gravity gradually slows it down. Then, as it approaches the moon, lunar gravity bends the spacecraft's path around the far side and redirects it back toward Earth. The key advantage is that this trajectory creates a built-in return route. Even if major propulsion systems were unavailable later in the mission, the spacecraft would still be on a path that brings the crew home. This also explains an important detail that often gets misunderstood. Artemis 2 is not going into orbit around the moon. The crew will not circle it multiple times. Orion will make a single close flyby. It will approach the moon, pass behind the lunar far side, swing around it in a long gravitational arc, and then head back toward Earth. In orbital mechanics, this is called a hyperbolic flyby. The spacecraft enters the moon's gravitational influence just enough for the moon to bend its path, but not enough to capture it into lunar orbit. That flyby matters because it allows NASA to test the exact kind of deep space navigation and spacecraft operations that future missions will rely on. The crew will experience communication delays, long-duration confinement, and the radiation environment beyond Earth's protective magnetosphere. At one point, Orion will travel farther from Earth than any human spacecraft has gone since Apollo, reaching well beyond the moon's far side. During the pass behind the moon, communication with Earth will temporarily cut off because the moon itself blocks the radio line of sight. That period is a normal and expected part of the mission, and it is one more test of how Orion performs without constant real-time contact. After the flyby, the mission enters its return phase. Orion will not need to turn around in the conventional sense. The flyby itself has already reshaped the trajectory. The spacecraft simply continues along the return arc created by the moon's gravity and begins falling back toward Earth. This is one of the elegant parts of lunar mission design. Once the trajectory is set correctly, gravity does most of the work. The final and physically most demanding phase comes at re-entry. Returning from lunar distance is very different from returning from the International Space Station. Orion will hit Earth's atmosphere at much higher speed because it has been accelerated by Earth's gravity during the return journey. That makes this a critical test of the spacecraft's heat shield, structural stability, and parachute recovery systems. The capsule must survive extreme temperatures and deceleration forces before splashing down safely. What makes Artemis 2 important is not that humans are simply going near the moon again. It is that NASA is finally testing, with a crew on board, the complete chain of deep space operations required for future lunar missions: launch, departure from Earth orbit, navigation through cislunar space, lunar flyby, long-distance life support, high-speed return, and safe recovery. If Artemis 2 works as planned, it will be the mission that proves the modern lunar architecture is ready for the next step: landing humans on the moon again. Thanks for joining us on this journey through some of the most incredible stories of science breakthroughs. If you enjoyed today's episode, make sure to give this video a like. It really helps the channel grow and lets us keep bringing you more stories like these. And if you haven't already, subscribe and turn on notifications so you never miss the next big discovery. We'd also love to hear from you. Which story amazed you the most today? Drop your thoughts in the comments below. We read them all. Thanks for watching, and we'll see you in the next Discovery Dispatch.